Alright, so we have this differential equation. R d theta plus R secant theta equals cosine theta. So when I'm looking at this, I see that it's a first order differential equation and it's linear. So secant theta equals cosine theta. If we rewrite it like this, we can easily see that every single term is at most to the power of 1, and the order here is given by r prime. So first order linear means that we can use the integrating factor. And for those who are not familiar, integrating factor is just e to the integral of px dx, where px would be this term right here. Okay, so let's just go about it and see what happens. So we're gonna have integrating factor e to the, well, let me start with the integral. So integral of secant theta d theta is going to be ln of secant theta tangent theta. Kind of just got to know that, but you can prove it if you're not a believer. Now we're going to raise that to the power of e. So e to the integral of secant theta d theta is equal to, since we have e underneath a natural logarithm, we can just take the inside. Secant theta plus tangent theta. Cool. So that's step 1, integrating factor. Step 2 is multiply the integrating factor to the entire equation. So secant theta plus tan times r prime plus r secant theta equals theta plus tangent theta cosine theta. Okay, so multiply the whole thing, and you don't have to do this, but I'm going to do it to show you why the next step makes sense. So I'm going to distribute this. So we're going to have, let me just copy this for save some time. Copy that, copy that. I'm just distributing. It's nothing crazy. Times r secant theta equals, let's leave that like this for now. Oopsie daisy. Okay. Well, let me just distribute this really quick. So cosine secant, that turns into 1. Secant, cosine times tangent. Tangent is sine over cosine, so you're gonna get just sine. So 1 plus sine. Okay. Now when you do one last distribution here, forgot the plus, but it's okay. You're gonna get secant squared theta plus secant theta tangent theta times r. Now, believe it or not, this is equal to the derivative of r times our integrating factor plus tangent theta by the product rule. So equals there, this. So when you do the product rule, you're doing first times the derivative of the second plus second times the derivative of the first. So here, this is exactly what you get. So first times the derivative of all this. Derivative of secant is secant tangent, and the derivative of tangent is secant squared. And then second, this part, times the derivative of the first. Derivative of r is just r prime. So that simplifies pretty nicely. So then 1 plus sine theta. And now you just integrate both sides. Oh, and we don't really care about the plus c when we do the integrating factor. Now we're going to care about it though. So Integral of a derivative is just, they inverse operations. They kind of cancel each other out. It's tangent theta equals theta, derivative of sine, it's going to be negative cosine. I mean, integral of sine. Then we add a plus c. Now we care about the integral for some odd reason. And when we distribute, we're going to be getting r secant theta plus r tangent theta equals theta minus cosine theta plus c. And let me check in the book. Yep. So yeah, this is the correct answer. But now we have to find out what's the largest, well, one of the largest possible intervals that we can have this solution on. Well, if you know a thing or two about trig, you'll know that, both secant and tangent have some domain issues. Cosine is fine, but secant and tangent we gotta watch out for. So let me just draw a quick graph of secant. So if we have a secant here, we have a discontinuity pi over 2, I believe. Oh no, sorry, this is for tangent. So tangent, we have, maybe you've seen this before. You have this kind of thing going on. Where it goes up to the next period. So that's tangent. Secant, on the other hand, secant looks something like, the way I like to remember it is you draw a cosine. Well, I kind of need more space then. Let me make this a little bit bigger. Ah, shoot. Make it a little longer so I can draw a full wave. The way I like to think about it is if you draw a cosine, secant is going to be secant is going to be looking like this with asymptotes where the cosine function is at its peak amplitude. I mean, sorry, at the middle of its amplitude. And that would be at, wait a minute, I think I'm doing this all wrong. Well, okay, no one's gonna ever watch this video, so no one's gonna know that I'm about to look up secant graph. And there's totally a million easier ways to do this. Oh, okay. At the peaks. Sorry. So, oof, forgetting my trig. It's been a while. So if you draw like, your standard cosine, we're gonna have peaks. Peaks are gonna be where the secant thing is formed. Okay, so something like that. And at this point here, recall that secant theta equals 1 over cosine theta. When is cosine theta 0? Cosine theta is going to be 0 at 0 or, oh no, sorry, pi over 2 or pi or cosine. This x is 1, so not a 0. It's going to be, yeah, pi over 2 k, or k is any integer. So we have these undefined points at these pi over 2 times any integer k. All this to really say that our domain is restricted to the interval from negative pi over 2 to pi over 2. and any other. So yeah, that's it. I guess another way you could think about it is that tangent theta and secant theta are kind of similar in the fact that tangent theta and secant theta are both over cosine. So tangent is sine over cosine, while secant is 1 over cosine. So we're kind of inheriting the domain restriction from having cosines in the denominator. So yeah, that's it. Thank you for watching.